Welcome. My name is Teacher Tumsime Tony, a teacher of physics and mathematics. So today we are going to talk about a new technique of integration, which is integration by parts. So we are going to see where this technique comes from, and when we are given a number on integration, we shall be able to see how do we identify that this number on integration requires us to solve it by integrating by parts. So this technique comes from the product rule. We know that if u and v are functions of x, we know that if u and v are functions of x, then what happens? If we differentiate the product of these two functions, we know that when we are dealing with the product rule tells us that we keep one function constant, we differentiate the other one, and we also keep the other function constant, we differentiate the other one. So it is v du by dx plus u dv by dx. This is what product rule tells us. Hope all we know this. So we are deriving this technique from this product rule. So what I'm going to do here, I'm going to integrate with respect to x both sides. So if I integrate with respect to x both sides, I will have the integral of vu dx. I'm integrating respecting x, remember that. So this is equal to the integral v du by dx with respect to x, then plus the integral of u dv by dx with respect to x. From here, this gives me uv equal to the integral v du, then plus the integral of u dv by dx with respect to x. So what I'm going to do, I'm going to take this function the other side such that I remain with the integral of u dv dx with respect to x. This gives me uv minus the integral of v du dx with respect to x. So this is the formula, or this is the technique, which is called integration by parts. So I'm going to explain a few things here. So if you try to look at this function, it is the function that is always given to us. So it means that it has two different functions, which is u and dv dx, of which those two functions, their product, we are integrating it with respect to x. So what does that mean? That if we have a function that looks like this, this is the way we always go for it. For example, I can give an example. If I have a function, say x exponent of x dx. So if you try to see this function, it is composed of two functions, this one and this one. So when we are dealing with integration by parts, we always choose a u, this u from this function. We always choose a u which is a function of x that is easy to differentiate. And when we differentiate that function, it is reducing. And we are always choosing the dv dx, a function which is easy to integrate. Because why do we do that? Because you see on our right hand side we have uv, yet here we have dv dx. So we shall always choose a function which is easy to integrate such that we can easily get our v, and we also have our u, such that if it is easy to differentiate, we are able to deal with this function here. This function here. It is the function that we shall replace here after differentiating this. Hope that one is okay. So let me get my duster. So I'm going to take you through a simple steps of how we can solve. So we need our formula. I can write it here. The integral of u dv dx is equal to uv minus the integral of v du dx with respect to x. So I'm going to use this one as an example. So if I have the integral of x, exponent of x dx, I'm going to try to relate this function with this. So according to the two functions I have here, I have an exponential function, and this function is a polynomial of degree 1, which is x, which is a line. So we see that this function is easy to differentiate, and this one is easy to integrate. If we choose, we also see that even exponent of x is also easy to differentiate. So for it, it does not change. It does not change. It's an exponential function, so it is easy to differentiate. If we choose our u to be exponent of x, it will be easy for us to differentiate it. But if we choose the x, it means that we shall choose x to be our dv dx, which will help us to find the v. Remember that if we choose our dv dx to be the x, we shall have v as x squared over 2, because we know if we integrate x, we get x squared over 2. So now it means that after getting that v, we shall replace it here, which is x squared over 2 plus du dx, which is exponent of x. And you see that we shall still have a lot of work to do on this function. So the choice is very important. So now we shall say, using integration by parts. So our u, we shall choose our u as x, so it means that our du dx is equal to 1. Hope we know that. Then, and our v, our dv dx is equal to exponent of x, such that our v will simply integrate to get exponent of x, which implies that if we have the integral of x, exponent of x dx is equal to uv, we have chosen our u to be x, our v is this that we have got, exponent of x, minus the integral of v du dx, which is 1, with respect to x, we shall get x plus x exponent of x minus, we know if we integrate this, we shall get exponent of x, then plus the constant c of integration. And the number is just easily solved like that. So let me show you, if we had chosen our u to be exponent of x, because it is easy to integrate, to differentiate, sorry. So our du dx would be exponent of x. And if we had chosen our dv dx to be x, then our v would be x squared over 2. This is x squared over 2, such that our integrand x exponent of x dx is uv x squared over 2 exponent of x minus the integral of v du dx. So you see that you still have another problem. Actually, this problem is bigger than this one, because you see that this function is increasing. So we always choose a u, which is easy to differentiate, and when we differentiate that u, it is a reducing function. Okay, so I'm gonna do another example. I'm gonna do another example. Suppose you're told to integrate, say, x sine x cos x with respect to x. So if you try to see this function we have here, if we try to use integration by parts, we can try to combine this as one function and this one as another function. But we know we can fuse this one. We know that sine 2x is equal to 2 cos x sine x. So it means that cos x sine x is sine x over 2. So we can have our integral equal to, so if this is our integral, this integral is equal to x times z sine 2x over 2. Then this one is easy to solve. This is a constant. We can easily put it here. This is a half integral of x sine 2x dx. Then we go. Then here we apply integration by parts. Integration by parts. If we apply integration by parts, we shall choose our u to be the x, because I know when I differentiate this is reducing. So du dx is equal to 1. Then our my dv now dx and my dv dx is sine of 2x, such that my v is equal to the integral of this. We know the integral of this is minus a half cos 2x. Hope we all know that if we integrate sine x, we get a negative x. Remember, this is a double angle, so we shall get that. So we can easily substitute in our formula we had previously. You can go back and check. So our integral, we have said that if we have the integral of u dv is equal to uv minus integral of v du, we simply replace what we have got here. So the integral of u will equal to a half into, because of this a half, so my u is here x, then my v is this what I've got, times minus a half cos 2x. So I'll put a minus here, then divide by 2, then minus the integral of v minus a half cos 2x. Remember what du is 1, du dx is 1, then with respect to x. That, so we have a closing bracket there. So we have a half into, this is minus x cos 2x over 2. Remember, this is a minus and this is a minus, so we shall have a plus. The integral, so plus a half into, the integral of cos 2x is a half sine 2x. So this gives us minus x cos 2x over 4, then plus 1 over 4 sine 2x, then plus the constant of integration. So we come up with such an answer. So integration by parts will always require you to identify the type of integral given to you. Usually you have two functions, they are different, and you have to choose the u and you have to choose the dv dx. And I'm going to give you a simple technique. How do I choose my u? You shall follow this one. We always first choose a u. So in your functions, if you see that you have a logarithmic function, this is a logarithm function, choose that one first to be your u. If you try to compare them, the two, if you compare the two, if you have a logarithm function somewhere, you just pick it as your u, because a logarithmic function is some kind very hard to integrate. So if you differentiate it, it will be simpler. Then this one, this is inverse. Then this is a trigonometry function. Then this is an exponential. So it means that what does it mean if I'm given such a function? Say I have exponent of x cos x. So I have an exponential function and I have a trigonometrical function. So when I'm choosing my u, I'll follow this order. So my trigonometry function here comes first before the exponential function. So I will choose my u to be cos 2x, and I will choose my dv, dx, to be exponent of x. As simple as that. So if I had exponent integration of ln x, you can try this one out and see whether it comes out, but I believe it comes out. So if I have a function like this, you're seeing one function, but there is a silent one here behind. There is a silent one there. To integrate this is very hard. So what you do integration by parts, where you shall choose your u to be the 1. No, not 1. To be the ln x. I've said if it is a log function, take it to be your u. So your u will be that, and you can easily get du dx, which is 1 over x. And you have your dv now, dx is 1, such that your v is x. Then you substitute in our formula, and you realize that you come up with a very good answer there. So before I close up, I'm going to give you a trial question. You're going to try it in your free time. So it will be so you're going to solve that in your free time. You will first deal with this. This is a cos squared theta, so it is a trigonometric function. We have an exponential function, but we know we have a way of making this one better. Put it in double angles, put it in form of cos 2 theta, and try to solve the rest. The rest is just simply following the steps. Okay, thank you so much for listening.